Dobry wieczór, prosimy już zająć miejsca. Ponieważ gościa mamy dzisiaj z zagranicy, to będę mówić po angielsku. Zatem welcome everyone. This is the next lecture in our series, Zapytaj fizyka or Ask a Physicist. Well, we are happy to see all of you here, especially that this is just the beginning of September, but nonetheless you are already here, so that's great. I hope this is a good sign for the whole coming year. And our guest today is Enrico Pajer. He is a professor at the University of Cambridge. He's a theoretical physicist and cosmologist, as you can guess from the title of the lecture, which is Making Sense of Making the Universe. He works to much extent on the universe, history of universe, and how it happened that we all happen to be here together now after several billions of years or so. So welcome in Warsaw, and stage is yours.
Okay, thank you very much, Piotr, for the kind introduction, and well, thank you, all of you, for coming here. I really love what I do for a living. I love thinking about the universe, talking about the universe, so it's great to have someone to talk to. And hopefully I will transmit and communicate some of that excitement and that I have for this field of research. I think it's really fascinating. You're all encouraged to ask questions anytime you like during the talk. Just shout out, question, and then I'll stop and I'll hear out your question. I see that there are a lot of young people around. You usually have the toughest questions, so don't worry, you can ask them. I'll try to do my best to answer them, and let's see where we get. So I thought I would tell you just 2 words about me, like who's this guy talking for an hour about the universe? That's me, I'm from Venice, I'm from Italy. My academic career took me around the world. I was in Germany for the PhD, in the US. I passed by the Netherlands. All of my children were born in the Netherlands. And I eventually landed in Cambridge in the UK. So that's where I'm coming from today. I'm a theoretical physicist. So that's the type of physicist that if you put them in a lab, that's dangerous for them and for other people. So I use with my pencil, my paper, and that's where I feel most at ease. I mentioned I have 3 kids. I promise I never do experiment on my own kids. So this is someone else. And this is a little bit of an outline of what I wanted to tell you about today. It's going to be an invitation to cosmology, why I think is so fun and exciting and surprising. So I'll try to convey that set of ideas, and then I'll try to tell you a little bit about what we know about our current universe, what has been its history and what's its content, and I'll tell you how we know it, because sometimes that's also the most exciting part is how did you figure that out? Like sometimes can tell you something is true. And finally, I'll tell you 2 of the most amazing things that I've learned probably in most of my life about the universe, and hopefully you will find them surprising and interesting too. Just wanted to spend half a second. So when I'm pointing with this invisible pointer, only those of you who can see really, really well can see the pointer. Hopefully that's not too distracting. I'm pointing at this picture on the top right. That's a picture that I particularly like because it really reminds me of why I like what I do. So those 2 people there are 2 of the most famous scientists of the first half of the 20th century. The 2 of them, they were some of the founding fathers of quantum mechanics. They revolutionized the way we think about the laws of nature. And I don't know, what does it think you of this picture? What do they look like? Yes. So to me, what they look like is they're really curious to know what's happening there. And they also look a little bit ridiculous in that position, the 2 of them at the same time. So it kind of reminds me why I do science, which is 1 is because I'm really curious about how it goes. And 2, because for me it's a way of playing with my brain, with my imagination, with my discovery potential. So I hope you can also have fun doing it. It doesn't have to be boring, but it should be really entertaining. So hopefully that's the spirit. So the one there to the right is Niels Bohr, and the one to the left is Wolfgang Pauli. So that's going to be the spirit, and let's jump into it. So this is an invitation to cosmology, which is this field of research that basically is about the most fundamental questions. So the first part is going to give you just a little bit overview of what cosmology is about. And one way that I'm going to try to introduce this topic is to think about the laws of nature. So we have investigated many laws of nature in many different fields of science. And one way to think about them is to think of some of the fundamental constants that exist in nature. One, which is perhaps quite famous, is the one represented on the vertical axis here. That is the speed of light. Usually physicists like to call the speed of light c. And although we don't do that when we drive our cars, we could measure our velocity in terms of the speed of light. You could say, I'm going to 10 to the minus 15 times the speed of light. Okay, so that's going pretty slow. Or you could go faster. And so when we study physics, we always want to ask the question, how fast are you going compared to the speed of light? And if you're going very fast, then we have to account a theory that was proposed by Einstein about 100 years ago that is called the theory of special relativity. Another important constant of nature, is just a fact about our universe, is this constant denoted with a strange symbol here. That's an H with a bar. The bar is a funny thing. Physicists don't want to really waste their time, so that should be h divided by 2 times pi, the Greek number and Greek letter. But physicists want to go quick, so they just put a bar, and so you remember there is a 2 pi there. And this represents when the laws of nature, they become very different from the way we know them, and they start behaving like the laws of quantum mechanics. That's a very different and non-intuitive behavior. It's completely different from the way nature behaves in this room, and yet we think that when you go to the size of an atom, that's the laws that you have to use, and that's what all of our devices are based on. The last constant of nature that I want to talk about was actually in some sense introduced by Newton, so it's called the Newton constant, is denoted with this Gn, and that tells us when gravity is important. In particular, gravity can be important in this room, otherwise we would be all floating around and bouncing off the wall. But sometimes gravity can also become very strong. And the stronger it becomes, the more important it is to have the correct description of gravity. And as far as we know, the best description of gravity we have so far is the one provided by Einstein's theory of general relativity. So this is the space of the most important fundamental constant. And why this three-dimensional space here is important is because you can think of various fields in science as organizing themselves in different parts of this space. For example, if you think of astrophysics, there is definitely things moving very fast. The accretion disk of a black hole is spinning around matter at very close to the speed of light. If you don't use the laws of special relativity, you will never get the right result. Astrophysics has very high velocity, so it's very high up. And the same for particle physics. We smash particle around close to the speed of light and see what happens at particle colliders. Instead, if you're doing a condensed matter experiment in which you're in tabletop, sometimes you don't have to have things that move very fast. For example, the waves in this table are not moving very close to the speed of light, and you can neglect special relativity. There are many other fields of physics. What I wanted to emphasize here is the strong gravity is never very strong in many of these considerations, and especially not general relativity is not needed. The same is true if we consider astrophysics, geology, condensed matter, and black holes. In that case, you really need to use the property of general relativity. General relativity can become very important because gravity is so strong near a black hole, and if you don't have the right description, you don't get the right answer. But typically, in none of these fields, you have to consider things that move very fast. Finally, the last plane in which the quantum mechanical effects are completely irrelevant to a large extent is the field of astrophysics, gravitational waves, and to some extent, cosmological measurement of the cosmic microwave background. There you can get away forgetting about quantum mechanics. The point that I'm trying to make is that when we are trying to think about cosmology and ask some of the most fundamental questions, such as where do we come from, why are we here, or why not, we will have to be really in the bulk of this space. We will be obliged to know about quantum mechanics because we are off on this axis, special relativity because we are off on this vertical axis, and general relativity. That's basically all the theories that humankind have developed so far to understand nature, and we will have to use them all to get the right answer. Now, of course, I realize that that's a lot of knowledge, and we will not assume that knowledge, but you should have in the back of your mind that there are many different ingredients that go into our current understanding of the universe. And that's why I personally find this field so exciting, because I get to use all the things that I've ever studied in my life, and I get to learn new ones every day. So really, you can think of the measurements that we make in cosmology that I will describe in a second. They are measurements about the distribution of matter, atoms, light, as well as new ingredients such as dark matter and dark energy across the universe, as really telling us about the properties of quantum mechanics and general relativity and their combined interplay, especially when we're talking about relatively small but precise effects. And so hopefully I will talk about it. This is a picture of the cosmic microwave background, which is, I will discuss in detail, is the best picture that we have of where light is distributed in the universe. And on the left, that's a simulation of how matter is distributed in the universe. And hopefully we will get to know those two pictures a little bit better. So before telling you too much, I just wanted to start the story a little bit at its very beginning. In some sense, you can say that cosmology started thousands of years ago when humans looked up at the sky and asked some very fundamental question, where do I come from? But in some sense, the modern version of cosmology has started about 100 years ago. And I wanted to walk you through the most important steps of this discovery because they give us the right canvas to paint the picture of the universe. So this is our current best understanding of what the history of the universe was, and hopefully by the next 10 minutes you will have some idea of what this is about. The main thing that you can see in this picture is that it doesn't look, we are somewhere here on the right, and we start making satellites and throw them into space and asking them to look very, very far. But you will notice that on the left, it looks like it doesn't continue forever. So that's perhaps one of the biggest surprises of the 20th century, that as far as we can tell, our universe is only a finite age, has not been around forever. But let's start from the beginning. So sometime, you can put the beginning wherever you like, a person called Edwin Hubble realized that he was able to tell the distance of certain specific stars. In general, in cosmology, telling the distance is the hardest thing. You might think, well, how hard it is. That's going to be 10 meters and maybe further away, 100 meters. But when we look at the sky, you don't know how big objects are. So you never know if something is nearby and pretty small or far away and really, really big. So the biggest problem has been that. But he thought, I think I know how to solve this problem because a colleague of his, Henrietta Leavitt, had studied it. And there are special stars called Cepheids, of which he was able to tell the precise distance. So he started measuring these stars and measured more and more of them and plot the distance on this diagram. So the distance is on the horizontal graph, and every time he found one, he put a dot here. He was also able to measure how fast these stars were moving, and some of these stars were in nearby galaxies. So when he was able to measure the velocity, he also wrote the velocity on the vertical axis. And then he looked at the plot and saw, oh, all of those points are more or less on the diagonal. I wonder what that means. So that was perhaps one of the most important discoveries written in this paper. He found that there was a correlation between distance and velocity. Using words, what he found was that the further away a galaxy is, the faster it's moving away from us. All of these galaxies were moving far away. It was as if everyone was running away from Earth. And the farther away, the faster they were running. It looked like we were at the center of something that was expanding. Eventually, he wrote down this relation in mathematical terms, and he says, well, the velocity, as far as I can tell, velocity v is equal to d, the distance, times a number. And I'm not sure he called it h, but it was called h because of his name was Hubble. So eventually, that is known as the Hubble constant. And this is a more modern version of that plot. And so this is a pretty useful information for us because it says, well, the universe is expanding, so things are going to get further and further away from us in the future. But it also means a few interesting things about our past, that things were closer and closer by. And physicists always like to ask extreme questions. Well, what happens when everything was just in a single point? And we will discuss that in a second. So that's why that discovery was so important. He found that the universe is not something static, but things are really moving, and they move in a clear direction away from us. The current value for this measurement is is written here, is 70 kilometers per second per megaparsec. So if you take basically the next galaxy away, which is roughly at the distance of 1 megaparsec, is running away from us at 70 kilometers per second, not kilometers per hour. So that's reasonably fast. There is something funny about the history of science, and I want to share with you, which I find it very entertaining. So we call this the Hubble constant, but it was not discovered by Hubble, measured by Hubble, and he was by no means the first one to write it down. In fact, often in science, people quote this nice thing that I didn't know was called Stigler's law, but in preparing this talk, I discovered. It says that no scientific discovery is ever named after its original discoverer. And after writing this slide, I realized Stigler was not the first person to write this law. Actually, it was someone else, whose name I forgot. Oh, Robert K. Merton, which makes sense. Perhaps we will find some exception to this, but more or less this happens all the time. In fact, Hubble had been scooped by Lemaitre, the Belgian priest, who also had met Hubble and they had discussion 2 years earlier. Imagine, for 2 years, that thing had already been known, and Hubble didn't know about it. Lemaitre had traveled around the world, had discussed with Hubble, knew about the measurement of the Cepheids, and 2 years before wrote a paper saying, well, I think the universe is expanding. Here is a model of the expansion, and here is a measurement of the constant that we now call the Hubble constant. Unfortunately, he wrote the paper in French. The paper is here on the left. I put the Belgian flag because he was Belgian. And internet didn't work so well. It was very slow back then, as you can imagine. So people didn't get to read papers from other scientists for a long time. It was Eddington in Cambridge who eventually realized how important the Lemaitre paper was and asked him 4 years later if he could translate it into English. Eventually he translated it, and this is the English version, which only appeared 4 years later. Even worse, in the translation, Lemaitre, when coming to a paragraph in which he had computed the Hubble constant, thought, this is a detail. I'm just going to neglect it and remove it from the English translation. So most of the English world reading his paper translated in English never even had any idea that he had discovered the constant 4 years earlier. Too bad. But we still remember him. And I'll mention a few more reasons why we remember him. This is a modern version of the Hubble diagram. Again, you have, well, I think this is flipped. So you have velocity on the horizontal axis and distance on the vertical axis. You still see it's a very tight relation. Actually, this is a modern diagram. This is measurements that have been made in the past 20 years. And scientists have been able to measure other stars that are much brighter than Cepheids. They're called supernova. In fact, they are exploding stars, so that's why they become so bright. Even a single star, when it's exploding, can be as bright as an entire galaxy. And by measuring them, they were able to continue this diagram at much, much larger distance, and they kept seeing a very tight relation, confirming the expansion of the universe. In fact, hidden in this plot, there is another major discovery of the 20th century that I will mention later on. Maybe you can spot it, maybe not. It's very hard to spot by eye. Okay, so we discovered that the universe is expanding. What do we do with it? I mean, we can talk about it, or we can try to make precise predictions about it. And so the idea was, let's model this mathematically so we can make as precise a prediction as possible. So we're going to predict the next thing that we should go out and measure. And various people have tried to write down this mathematical model. Here we are talking about the 1920s, so it's already 10 years after that Einstein had written down his famous equations, the Einstein equations, the equations that govern all gravitational phenomena. When Einstein wrote them down, he didn't really have in mind the whole universe. Perhaps, like Newton, he had in mind at the beginning the planets that orbit the sun. But the power of the generalization that we do in physics is that if you're describing gravity, you're describing all of gravity, whether it's a star around the galaxy, whether it's a galaxy around a cluster of galaxies, or whether it is the entire universe. And so these people took him seriously. They said, if these are the equations for gravity, we are going to solve them, and we should find a solution that represents our universe. And so they did. The first one to do is, so clearly we mentioned that Lemaitre already did it in 1927, but he himself had been scooped 7 years earlier by the Russian mathematician Friedman. was here, who also had written that paper that was completely unknown. No one in the Western world, or perhaps outside of his own research institution, had ever read this paper. Eventually today, this mathematical model is named after these two persons, plus the other two American physicist mathematicians that generalized their model as the Friedman, Lemaitre, Robertson, Walker model, which is very long to say, so people call it FLRW. To this day, this is the best description that we have. The model is quite simple, but is within the language of Einstein's theory of general relativity. However, the idea is so simple that can be shown in just one picture and one formula. This is basically the model. Imagine that the universe is a rubber band, and various points, you just mark them with a marker on it, and you call some point 0, some point 1, some point 2, 3. The universe is just expanding like the rubber band is stretching. So there is literally space being created between any 2 points at any given time, and space continues to be created as the universe becomes bigger and bigger. If you're sitting on the rubber band, you're not moving away. You just sit there, but you get further and further away from another point on the rubber band, even though you're not moving. In this sense, we are really talking about the expansion of the universe as a phenomenon of space-time, rather than as the motion of objects. And mathematically, actually, there is basically a single equation that you have to remember to describe this model. Every time you see a distance in cosmology, let me call this distance r. For example, it could be 2 megaparsecs, that's the distance to the next galaxy, or 200 megaparsecs, that's the distance to the next cluster of galaxies. You should multiply times a function a of t that tells you how much the universe has stretched. If a is 1, then the distance is just the distance. If you wait until the universe stretches twice as much, that object is going to be twice as far, or 3 times as far, and so on. The whole model is down to this. Actually, it didn't really take Einstein general relativity to figure it out, but this model really gives you many other predictions when you use general relativity. But it's just as simple as this. One thing that I love about this model is that it's so simple, and yet just when you say it, it implies something quite dramatic. If every distance should be multiplied times a of t, what happens when a of t is 0? That's the type of question that physicists love to ask. They're just extreme questions. What happens when a of t is infinite? What happens when a of t is 0? Well, when a of t is 0, every distance has to be 0, because 0 times any other number is 0. It's very simple, but what do we call? Well, if there ever was a moment in which this function of time that tells you how much the universe has stretched is 0, we call that time the Big Bang. The Big Bang is something that is a lot in public culture, and people talk about it all the time. And sometimes this is the type of pictures that people draw when they talk about the Big Bang. So you imagine a big explosion. Actually, the name itself means big explosion. But the Big Bang is not really a point in space. There was not a point from which stuff was exploding. The Big Bang is really a moment in time. So next time you think about the Big Bang, you should think of a clock. It ticks. And at some point, it started and kept ticking. In fact,
I have a question.
yes?
So, well, is there like, okay, so I'm like, never touched this field, so I'm experiment this, but I just want to ask you, is there like kind of distances which expand and the kind of other distances which do not expand?
Yes, there are. So to be much more precise, it's only cosmological distances that expand. As far as you understand, when there is an object which creates a bound state, for example, the atoms in your bodies and the molecules in your body, they are bound to each other, they are not expanding. The same for our solar system, which is made of the bound orbits of planets, is not expanding, neither is our own galaxy, which is a bound gravitational system. But when you talk about systems that are not bound, either by gravity or by other forces, then they will be expanding. And so the correct way of thinking about this expansion is an expansion among galaxies. You're welcome. Some other questions? Yeah.
Sorry, if it is for
No, please go ahead.
anybody. Anyway, I'm going to ask.
No, go ahead, yeah.
So, well, like, is it only like, if you have a free body, and if it is not bounded by gravitation, then only it moves, or it is
Okay, well, you can have a discussion at the end if you elaborate. Yeah, that's good. So one of the questions when people say that it is expanding is what is expanding into? And there are various answers to that question. The answer that I like the most is that it is expanding into the future and is expanding away from the past. So the way I like to think about it is that the center is the very past, as far past as you can, the center of the circle. And as you move away from the center, the distance from the center represents time. So let's say now is the blue circle that you see here. That represents the present. And on that blue circle, along the circle, there is me somewhere, another star somewhere. Here I've drawn two stars that are almost invisible. So one is on the blue circle and the other is somewhere else on the blue circle. In the past, this blue circle was smaller and smaller because the universe has been expanding. And in the future, this circle will be bigger and bigger. So in some sense, the expansion is happening into the future. The very center of this drawing is the Big Bang. That's when the full circle had the size 0. It's shrunk down to a point. All the stars on that circle, no matter how far they were, they all have distance 0. That's what we call the Big Bang. That's when the laws of nature as we know them, they stop being valid, and that's where much of the research is pushing us towards. There is another thing that usually people feel uncomfortable is that, well, you told me that the velocity is equal a number times the distance. What if I go very, very far? Yet another question that physicists like to ask. Well, if r is so big, at some point that velocity is going to be faster and faster and faster. Can it be faster than the speed of light? Why not? If r is just bigger than c over h, then I just multiply, and that's bigger than c. And c is the speed of light. That's exactly correct. That's precisely what happens. And, okay, the envelope. And that's not the problem. As far as we understand, what we are describing here is that the distance between 2 points is increasing very fast, but there is no communication between one point and another. The real interpretation of that there are places in the universe that get further away from each other faster than the speed of light is the following. Did you have a question? There is no center. Did you ask where is the center? So the reason why in the previous drawing I drew it as a circles was to try to emphasize that now there is no center of the blue circle. Any point on the blue circle is the same as any other point. So maybe the only answer to your question is the center is the past, the Big Bang. But now is just the blue line, there is no center. There is only, you're just on the circle now. I hope that helps. Could you speak up a little bit because it's hard to hear? That's true. So you have to imagine generalizing a circle to, let's start, a circle is one-dimensional. If you generalize it to 2-dimension, you know what it becomes. It becomes a sphere. And mathematicians are very good at making things even more general. And they said, well, what if we generalize it to 3 dimensions? And they think of a 3-dimensional sphere. That's hard for us to draw on a piece of paper, but it's a perfectly well-defined space. And it is possible that we are living on a 3-dimensional sphere. In fact, I can say more about that if you'd like. However, if you don't like thinking that we live on a sphere, you can think that we are living just in a space that is infinitely big in all directions. So it also doesn't have a center. Excellent. Yeah, some other question. Oh, yes, please.
If the universe were to shrink, would it go back in time?
As far as we understand, no, it wouldn't, because there is another important law, which is called the law of thermodynamics. And it says that things get more messy rather than tidier, like our rooms or our cars. And so as far as we can tell, everything in our universe is increasing its entropy. And so even if the universe started shrinking back, that entropy has already increased. All the glasses that have dropped on the floor by accident will not get back together. So as far as we can tell, no. However, there is another interesting part about your question, which is, will it ever shrink back to itself? And so far I haven't told you, I just told you it's expanding. But we will see in a second that we have a hint of what will happen in the future, whether it will keep expanding or not. Excellent, yeah, good. Some other question? Oh, yes, please.
So, at the distance that the universe expands faster than the speed of light, there is no possible communication between us and this.
That's correct.
So, we just,
Sorry. Please use microphone again.
So, can we just assume there's nothing out there?
That's an excellent question. That was exactly my next slide.
Oh, all right.
So it's the same question. So from here, if I just went on the top of this building, do you think I could see New York? No, because the Earth is too round, right? We have a horizon. I think that I read somewhere that if you're just standing somewhere at 5 meter height, your horizon is of order 10 or 20 kilometers or something like that. And yet we believe New York is there. I was there a while ago. So in cosmology, we have this concept of a horizon, which is due to the fact that there are places in the universe that cannot send us any signal. We cannot see them because exactly as you predicted, even if they send us light, it would never get here because they're getting too far away from us. And yet they're probably there, we just cannot see them. This is the concept of cosmological horizon. This is my drawing of the normal horizon on Earth, but there is a different type of horizon, which is the cosmological one. So this is what you had in mind. We are somewhere at the center, and there is some distance from us represented by the dark circle, beyond which, even if something sends us light, it would never get there. That's called the cosmological horizon. And it's, the distance from us is about 14 gigaparsec. So it's 14,000 times the distance to the next galaxy. If you went that far, we wouldn't talk to you anymore, and you wouldn't talk to us. We have no reason to believe that something dramatic happens there, that there is a border of the universe and everything dies as it goes through. As far as we can tell, maybe the universe just keeps going. It's just that we cannot communicate with it. So that's another deep implication of this very simple model. So even if it was so simple, it has already two implications. One is that perhaps there was a beginning, a Big Bang. And two is that we cannot really answer the question how big the universe is. We can only answer the question, how big is the universe that we can see? And outside, it could be infinite, it could be finite. We really have no scientific way to address that question. So that was a great intuition. Yeah. Yes, please, the last question, and then I'll continue. Yes? Yes. Outside of our horizon?
No. If we get to the other like star, and we stay with this star, that means that our, for example, Earth, it's getting away from us. So does it mean that this star is getting away, or this or our Earth is getting away?
Oh, yeah, that's a good question. So if you went to another galaxy, for example, the next galaxy is called Andromeda. That's about a megaparsec away. And if you went there, you thought that the Milky Way is getting away, while we would say, no, it's you going away. And as far as we can tell, there is no way to tell who is right. That was, to some extent, Einstein's first intuition that there is a relativity about motion. And even if you were accelerating, to a large extent, we wouldn't agree. You would say, no, you're accelerating. I would say, no, it was you. So it's relative who's describing. So I think the answer is that there is no good answer to that. We both have the right to have our own way of saying it. Yes, I think I have to go on because they told me that I have to stop. Yeah.
Okay, so well, everything is expanding, and is it possible to track the trajectory so that you can see where this Big Bang happened?
There is nowhere. If you just stare enough at this drawing and ask the same question for this, if you just go back, when you go back, if you stare enough at this drawing with the circle and ask the same question, you will see that there is no single point on the circle, blue circle, where all of those dotted lines meet. They only meet at the very center, but the center is a single point, so you cannot tell where it happened.
Okay.
Excellent. So these are really good questions. And so I'm going to move on to tell you something even crazier than this, if you can believe, even crazier than the expansion, which is, well, okay, so we have all of this space-time is expanding, but what's in there? What's the content? Well, I mean, you say, well, I know one thing. There is atoms. I know I'm made of atoms, so there should be atoms. People have actually tried to ask this question by making measurement and trying to say, okay, how many atoms are there? And they found, again, the most surprising answer. So they went out there and they say, okay, let's measure how much there is. We're going to put it on a pie chart. The bigger slice is the bigger quantity. On the chart, what's actually shown is the energy density. And when I say energy, it's the same as mass, according to Einstein's famous equation. And then they said, okay, let's count the total up. How much of it is atoms? Oh, 5%. What about the remaining 95%? Well, astronomers and cosmologists went out and say, well, 26 or 27% is also matter, but is not atoms. Cannot possibly be atoms. What's even worse, there is some other 68, about 70%, that is neither matter nor light, and we don't really know what it is, but when you measure it, it's surely enough, it's out there. So I wanted to tell you more about this and why it's so surprising. What's so surprising for me is that you think, whoa, most of it should be atoms. We are just a small fraction. 1 part in 20 of the energy density of the universe today is made of atoms. So what's the rest? So the biggest chunk here is called dark energy, which is more of a name than an explanation, but that's as much as we understand at the moment. That's 70% of the total today. It was really discovered in 1998 by looking at that same picture that I showed you of the modern Hubble plot, the one with all the supernova dots very tight. If you had looked at that picture really, really, really closely for probably a few months, you would eventually have noticed that there was some particular property to our acceleration, to our expansion, that our expansion was slower in the past than it is today. In particular, it means that not only the universe is expanding, but it's expanding faster and faster every day. We had sufficient data to discover this only 25 years ago, in 1998, 26 years ago. It was a big discovery. It says not only it's expanding, but it's accelerating. And this addresses a question that I got from up there. What happens if it started crunching back? Well, it could happen one day, but for the moment, it's doing exactly the opposite. It's shooting out. So it looks like it's expanding even faster rather than coming back down. Whatever generates and sources this expansion, we don't know, but we like to give names also to things we don't know. And this thing, we call it dark energy. It's called dark because no matter how long you stare into space, you will never see it. It does not interact with light. As far as we can tell, there is no way to see it with light. In fact, maybe it doesn't emit light, it doesn't absorb light, it doesn't interact with light, it doesn't even want to talk about light. In some sense, it should be called more transparent energy, but it's not as catchy, so people call it dark energy. As far as we know, it's everywhere. Everywhere there is space, there is dark energy. And it's an incredible substance. It behaves differently from any other thing. So for example, if you take a box and put inside, let's say a diamond, and you make the box twice as big, how many diamonds do you expect to find inside? Still one, otherwise we would all be very rich. Dark energy is different. If you put it in a box and you put some amount and you make the box twice as big, you find twice as much dark energy inside. Wherever there is space, there is dark energy. So it has these very strange properties, and we still don't understand what it is, and we don't have a microscopic description of it. One idea was thrown around by this man about 100 years ago, but very soon he said, nah, this is nonsense. It's definitely wrong. So the first idea to be proposed, even before there was a discovery of the accelerated expansion of the universe, was by Einstein, who proposed the existence of a cosmological constant. So he said, well, there are many constants of nature. There is the speed of light. There is the constant of quantum mechanics. Why not a new constant? This is the constant of how much energy density there is in the universe. He actually put out this idea for a completely opposite reason. He didn't know the universe was expanding, and he really wanted to show that the universe cannot possibly expand. And so soon after writing the paper, he called this the biggest blunder of his career, so the biggest nonsense he ever said. 100 years later, this is our best candidate of what dark energy is. People are still trying to see if it is really a cosmological constant or if it's something more interesting and exotic. But as far as we can tell now, it just appears to be a constant of the laws of nature as we know them. Okay, so that was the first big chunk. So we got away with describing 70%. I didn't say much about it, but at least I gave you a name. Not as much as we know today. The other chunk, which is this 25%, 26, is called dark matter. As the name suggests, it's matter. It should be some kind of stuff like atoms that moves around. You can say where it is. You can kick it around. The thing is that it is dark again. So no matter how far and how long you look, you're not going to see it with your eyes. We have to see it in another way, through its indirect effect on other things. The first person who had the idea of the existence of dark matter was Zwicky. He was studying the Coma cluster, which is a cluster of galaxies, and he was seeing this galaxy going around and around, and then he did the calculation and thought the only way that this galaxy go around is if there is a force, a gravitational force pulling them towards the center. But there wasn't enough matter to create that force. So he created the idea that maybe there is a dark form of matter that we don't see. This was the 1930s. He was way ahead of his time. And he was also not a particularly nice guy. So he was famously heard talking about his colleagues as spherical idiots, because they are idiots no matter how you look at them. So clearly this didn't make him very popular, and his ideas never really caught on or were very confirmed by colleagues. When people started really taking this seriously was only 40 years later, when Vera Rubin and Kent Ford measure how galaxies rotate. They were able to get much more precise measurements. It was a similar idea. Instead of looking at a bunch of galaxies rotating together, they looked at a bunch of stars going around the galaxy. And they said, well, if the matter is the one we see, the line of the velocity of the stars, which is on the horizontal, compared to the distance, the velocity is the vertical, compared to the distance from the center of the galaxy, should be this dotted line. They went out, they measured, and sure enough, it wasn't. It was a very different set of data. It was the set of data that you see on the yellow dots and then blue dots. The only way that you can describe those stars going around the center of a galaxy so fast is that if there is something else that is pulling them in that we cannot see. So this has been confirmed for hundreds of different galaxies, and many other pieces of evidence for the existence of dark matter have been collected through the years. So our current pictures of what dark matter is the following, that every time you see a galaxy, or perhaps you use a telescope to see a galaxy, sure enough, the galaxy is there, but is surrounded by a very large halo of dark matter, a very puffy cloud of dark matter that occupies maybe 1 million times more space. And it is that dark matter that helps the galaxy going around the way it does. We know very little about dark matter. I can tell you it's matter, so it's really like just clumps of stuff moving around. However, if you ask me how big is it like this big? How much does it weigh? That's the most uncertain quantities in science. As far as I can tell, I've never heard of any other scientific quantity that is as uncertain of this. It is uncertain by 80 orders of magnitude. So you can change it by 1 followed by 80 0, and you can make it that much bigger, and it still describes the universe as we know. Some people go around saying, oh, it's definitely made by black holes the size of the sun that we just don't see because they're black. And some other people say, oh, that's nonsense. It's made by ultralight particles called axions that have a mass which is 10 to the minus 27 times lighter than an electron. And both could be right, as far as we can tell. Funny, huh? So was there a question? Yeah, please. Please. So there are various types of galaxies. Usually people talk about the morphology of galaxies into 3 categories. The ones that are somehow flat, they call them pancake-like, like the Milky Way. They usually form a disk, and the disk is a bit larger, but there is not much on the top. There is a second category that are called elliptical. they look more like an egg. And I love this part. The third one is everything else. Everything else, they're called irregular galaxies, and they have a wide range of different morphologies and shapes, and astronomers describe them in great detail. So that's roughly speaking why. But you're pointing to a good point that galaxies are much flatter, pancake-like than dark matter is. Dark matter is much more like a puffy cloud, and there is a real reason to it, which has to do with radiative cooling processes that I can tell you more about. Okay, finally, after talking about 95% of the universe, we finally come to us. We're made of atoms. That has to be there. It's about 4% of the total as far as we can tell today. And this is the stuff we are made of. Actually, most of atoms are not really visible in the sky. They're made of very diluted gas that is between one galaxy and the next. There is also light. We usually think of light as the one we see, but of course, light is any form of electromagnetic wave. That's what the big insight of Maxwell from the 19th century, from microwaves to radio, from X-rays to gamma rays that make you becoming the Hulk. Those are all forms of electromagnetic waves. And the universe is filled with them. Surely we see the light coming from other stars. But what was discovered about 50 or 60 years ago is that most of that light, if you just count how much there is in the form of what is called as the cosmic microwave background, mostly often shortened as the CMB. And this is a picture of the cosmic microwave background. This is coming from the fact that the universe back then, back in the day, because of the expansion, was very small, but also very dense. When it got very dense, it was also very hot, and just like a piece of coal, it was glowing hot. All that glowing was light that started traveling during the early universe and is still traveling around today, and we get to capture it, and we call it the cosmic microwave background. It was discovered by Penzias and Wilson in 1967, and it is the strongest piece of evidence that the universe is expanding. Because otherwise, what else would have generated this almost thermal shine that we see in every direction? This is coming really from every direction. It's not possible that it's not coming from a star or from a galaxy, in every possible direction. It turns out that our friend Lemaitre got to know about this discovery 3 days before he died. So he finally knew that the idea he had of the universe that is expanding was probably correct, as had been suspected. The story of the discovery of the CMB is fascinating. It's the story of a few theoreticians who knew it was there, went out to measure it, but they were theoreticians. They weren't very good at measuring. And the stories of experimentalists who had no idea it was there, but they were very good at measuring things. And they really believed what they measured, and they found it first. At least they gave a phone call to the theoreticians and told them about it. And they realized they had been scooped. So this brings us through half of our story. We know we have some idea of the history of the universe, and we know what's there. I wanted to tell you 2 more things about this. They're a little bit more advanced, but I think they're really fun to think about, and they connect a little bit more closely with the type of research that is done nowadays, even though all of this is related to current research. So the story it goes as follows. It's about the functions that originated the universe. So far, I mostly talk about what there is in the universe and that it is distributed everywhere. But it would be nice to be a little bit precise about where is this stuff. Where are these galaxies? Why is there a galaxy here rather than there? Why is a little bit more light or more dark matter in one point rather than another? And when you try to ask these questions, you always come back to the same answer, which is, well, it is here because before it was there, because before it was there, and before it was there. So you have to tell me, how did it start? If you tell me how it started, then I can tell you where it ended up. So we're talking about the initial conditions. How did the universe start having this thing distributed in one way or another? And that's the type of question that we want to ask. These questions, even though none of us was around in the very early universe, we have good pictures of what was going on. One picture is this picture of the microwave background. So in that picture is a picture of the universe. In some sense, it's a picture of the baby universe. If you think of the baby universe as being a 40-year-old person, that's a picture 4 hours after birth. So it's tiny little cute baby universe. And it looks like it has different temperature of light in different directions. Red means hotter, and it represents 300 millikelvin, and red means colder, minus 300, sorry, microkelvin. And so what generated those differences? Why is it a bit hotter here or a bit colder there? We also have good pictures, and increasingly good pictures, of the distribution of galaxies. Every single dot in this picture is a galaxy that has been measured by a spectroscopic survey. This particular picture comes from the DAISY, the Dark Energy Spectroscopic Survey. And they have 35 million galaxies, so much so that they don't fit in the picture. They only put 40,000 to make this one, and it was already high definition enough. So we really have measured a bunch, and we see all of this distribution. How do we understand that there is no galaxy in this little black spot and there is a bunch in this little bright spot? What generates this distribution? Yes, please.
Question that from this microphone. Okay, so it's working. How it's possible to get minus 300 kelvins, microkelvins?
Oh, sorry. Yeah, excellent question. I said it in a very confusing way. Yeah, you're right. Is there a piece of chalk? No. The right answer that I should have said that it is 2.7 Kelvin plus or minus 300 microkelvin. So the temperature is 2.7. So it has an average temperature, which is 2.714159 Kelvin. And this 74124. So this last digit, they change from point to point. And those colors represent the little change here. But the average temperature is 2.7. So that's the best answer that we have to what is the average temperature of the universe in some sense. It's about 3 Kelvin. So there is a good, thanks for pointing it out. There definitely is a plus in front of this. Yeah, thank you, please.
So I was wondering about the fact that like there is a humongous irregularity when it comes to our universe, and it's an irregularity between matter and antimatter. And
Yes.
I wonder where does this come from, and also because like if it wasn't for this, we wouldn't be speaking right now.
Yes.
But why this irregularity happened?
Yes.
Do physicists have any theory?
They have many theories, but none of them is known to be right. So when you have more than one theory, that means that probably you don't know. And I would say that there are maybe at least 3, 4, or 5 different explanations. And the short answer is that we don't know. The longer answer is that we know how it's possible to write down a theory such that that happens. But the theory that contains all the particles that we know of is not sufficient to make that happen. So there must exist new laws of physics that go beyond the one that we have been able to measure in collider experiments. And those new laws will make this possible. In particular, there are specific conditions known as Sakharov condition that allowed for this to happen. This process that you're talking about is known as baryogenesis, because physicists call particles like the protons and the neutrons, they're called baryons, and most matter is made of protons and neutrons, and so baryogenesis is the genesis of baryons. And people don't know how this came about. But you can write down various theories that go beyond our current understanding in which this happens. Knowing which one is right is beyond our current capabilities. But there are some ideas. If you want to look more this up online, you can look for the keywords leptogenesis, for example. Yes? You're next.
Yes, so we established earlier that since the Big Bang, space was expanding outwards, away from us, and all points were moving away from us. So I am wondering how come that we can capture images of this cosmic microwave background radiation. Shouldn't it be moving away from us and not towards us?
Well, light, if you're running away from me and turn on your lighter or your phone, I still see the light because light shines in all possible directions. So it is true that on average you and your phone are moving away from me, but light comes out of your phone in all possible directions. And since light is faster than you, it still catches up with me. So the light of the hot universe was shining in all directions, and some of it just happened to be shining towards us. You're right that most of the light was shining elsewhere, and if we go somewhere in another galaxy, we would see another picture of the cosmic microwave background, and another picture somewhere else.
So actually, I have heard about a model, which is like, if I am correct, so it is a condensate model of intergalactic medium, something like this.
Okay.
Okay, and it is something like, it describes the matter, which is ziggling between the galaxies like a condensate.
Okay.
Okay, so, and here I heard about this idea of expanding universe, so I'm not sure that if some matter which is accelerating, it has acceleration in kinetic energy.
Yeah.
So
I think we should postpone maybe a discussion in private
okay.
after, so that we
So
can
it
get
is-
through most of this story. But thank you for your interest and excitement on the topic. I was going to say a couple more things, if that's okay. I don't know who's chairing, but you kick me out when it gets too late. And so I wanted to come up at least to a different type of the story. So we want to try to understand how things are distributed and why they are. This is a computer simulation of how we think they might be distributed. Every dot represents some dense distribution of dark matter. And to answer this question, we said we have to go back to the very beginning, because it's always what happens before that determines it. So what happened at the very beginning is a new process that we didn't discuss that is known as cosmic inflation. And this idea is that in the first fraction of a second of the Big Bang, the universe expanded enormously, and a lot of the space that we see today was just generated during this very fast expansion. This idea goes back to the 80s, and now by Alan Guth and many other people like Linde, Starobinsky, Steinhardt, Albrecht. And now has gained a lot of attention because it leads to other predictions that we can confirm. And so to try to answer the questions that we have, why are things distributed the way we see them, we have to go back to inflation and try to answer during this very fast expansion, how did things get distributed? And here are two crazy things that I wanted to tell you about. Hopefully I'll have time to sketch them. This is a quote from Niels Bohr, which is the same guy that we saw at the beginning. So he told during a seminar, he stood up, he says, yeah, this is, your theory is crazy, but it's just not crazy enough. It's probably not right. Nature is really surprising in how things work, and some things are completely the opposite of what we would have thought. So here I'll show you two things that I think are very different from how I thought they would have been in our universe. For the first one, imagine that you're going to buy fruit at the grocery store or the supermarket, or imagine the fruit that you have at home. There are many people here, each one of you has a home, some of you has a bowl of fruit somewhere on their counter. Mine definitely doesn't look so neat and colorful, but these are the images that I found. Turns out no one posts very ugly images of their fruit bowl. You might think that different people have different fruit bowls. Some people have like a lot of bananas, they really like bananas. Some people have only oranges, they really don't like apples, for example. What would happen if you went into everyone's house in this room, and in everyone's house you found exactly the same fruit bowl? It looks exactly identical. It's just in one, all the apples and all the pears and all the kiwis are slightly smaller. That would be really strange. Well, it turns out that our universe is like this rather than like that. Let me explain. Imagine that bananas that I'm talking about, they're actually galaxies. And watermelons, they're actually dark matter. And apples is the fabric of space-time. And ananas is light, and so on and so forth. And kiwis are neutrinos. Well, we have been looking at the sky and see how they are distributed across, and what I would have expected to find is that, well, they started off however they liked. Bananas could be more here and less there, when apples could be a little bit the same, and pineapple completely different. So this is what I would have expected to be, that there were many different functions to describe the distribution of all of these constituents of the universe. But cosmologists have been looking now for at least 30 years, and this is not what they find. To their enormous surprise, what they found is that everything is distributed in the same way. In the place where you see a lot of bananas, there are also going to be a lot of oranges and a lot of kiwis. In other words, where there is a lot of dark matter, there is a lot of matter and a lot of light, and the same for when there is less. Their distribution is all attached to a single function. So our goal in trying to understand how stuff is distributed across the universe is just to understand the distribution of one of these things, because all the other will be the same. So that is one completely mind-blowing. I don't know why this had to be the case. Scientists have some proposals, but again, they have at least two proposals, which means that they really don't know which one is right. And one of the proposals goes under the name of single field inflation, if you want to know the keyword. But the real answer is that we don't know why this is the case. This is one of the big open questions that our generation is trying to face. And the second big question that I wanted to discuss, okay, so the dysfunction as an, oops. All of you keep your fingers crossed. Yes, good job. Good, so the other mind-blowing thing with which I wanted to conclude this presentation is, okay, we know that we have to describe just a single distribution of stuff, but where does this distribution come from? Why did the universe start having a little bit more things here and less things there? Eventually, when there was more things there, a galaxy formed, where there was a little bit fewer things, then there was a big empty space, which is the space between one galaxy and the next. But why did it start that way rather than somewhere else? And here, physicists came up with the craziest answer. And they said that the answer to this question is quantum mechanics. And that's nothing to do with atoms, nothing to do with the way your computer works. We're talking about the distribution in the universe, and yet we think that the same principle that explains atomic physics and subatomic particles also explains the distribution of matter in the universe. And so for that, I just wanted to quickly say a couple of words about quantum mechanics. These are two of the founding fathers of quantum mechanics, Heisenberg and Schrödinger. And by the 1900s, physicists felt really good about themselves. They had a theory for gravity, which was Newton's law. They had a theory for thermodynamics that fueled the Industrial Revolution from Boltzmann and Gibbs, and they had a theory for electricity and magnetism from Maxwell, Ampere, and Faraday. So they said, what is there more to do? Maybe we should just all go retire, go on vacation. Physics is basically solved all the questions. And that's when everything they knew fell apart. And the two biggest development in theoretical physics took place. One was the understanding that when you try to describe very small objects like atoms, none of these laws as we know them actually make sense. And Schrödinger and Heisenberg had two completely different insights into this problem that turned out to give the same theory at the end, which was later developed by many contributors such as Dirac and von Neumann and many others. So what is the main idea? Well, to understand this main idea, let me just start with the simplest object that physicists like to talk about, which, believe it or not, is a pendulum. I've never really owned a pendulum. I don't know if people own pendula. It's not a common object, but physicists really want to talk about this object over and over again. In fact, there is a famous physicist, Sidney Coleman, that he said his whole career and the career of every theoretical physicist was about describing a pendulum, which he called harmonic oscillator, in ever increasing levels of abstraction. So physicists really like this system because it has a very simple motion. It goes back and forth, back and forth. However, as you know it, you can just take your hands and stop it. Just put it there and stop it. Or you wait maybe 5 minutes, it will stop by itself. So what's the big deal? What quantum mechanics says that stopping a pendulum is actually impossible. If that pendulum is small enough, the size of an atom, such that the laws of quantum mechanics starts having a large effect, it's actually impossible to stop. So this is a classical pendulum. Imagine that it is as small as an atom. You just stop it from moving. You know exactly where it is. It's right here. And you know how fast it's moving. 0 velocity. So what's the problem? Well, Heisenberg came along and in a very complicated paper that no one understood for at least 10 years said, actually, he never really said this, but this is how people understood what he was talking about. He said, you cannot know the position and velocity of something at the same time. In fact, this is how he was talking about how to find the car keys with his partner. partner couldn't find them. He says, well, maybe you know their velocity too well. If you give that up, you will find them. That was the birth of quantum mechanics, but that really means something for us. It means you cannot stop a pendulum, because if you stop it, you know where it is, you know how fast it's moving, and that violates the starting assumptions about quantum mechanics. This is the key idea of quantum mechanics that can develop in a very rich and intricate formalism, and we're going to push these ideas towards space-time. If I cannot stop a pendulum from moving, or a particle, or any other physical entity, well, space-time is a physical entity, so space-time itself cannot stop from oscillating. So if you really zoom in into space-time, and you zoom, and you zoom, and you zoom, and you went to the smallest possible distances, the distances of an atom, or much subatomic distance, space-time itself should always be oscillating. This picture of what space-time is perhaps the biggest headache that physicists have had for 100 years. How can I explain space-time if it is oscillating? After all, space-time is about being somewhere, but if somewhere oscillates, where is it? And we don't have good answers to these questions, but we believe that at least an approximate treatment is within the realm of our current possibilities. And when you do this, you know that the initial universe during inflation couldn't have been perfectly homogeneous. Things were always oscillating back and forth. There was no way to stop them. And it is those quantum oscillations that eventually led to a galaxy being born rather than a big empty space, that eventually led to a planet forming rather than the big space that there was among the planets, and then eventually decided how everything was distributed across the universe. So our current understanding is that the distribution of everything came out of quantum fluctuations. And these quantum fluctuations we can describe very precisely, and as far as we can tell, our description is matching precisely what we measure. And now coming to the last slide, and I will conclude with this, is that you might have heard about other forms of fluctuations of space-time, especially because they have received a couple of Nobel Prizes in recent years. Sorry, maybe just one, but they will receive another one within 2 years, which is gravitational waves. Other type of fluctuations of space and time, they are detected with huge so-called interferometers that look like this. They send a laser like this back and forth, and they see when it has a delay. And so will the early universe also generate this type of gravitational waves? This is one of the biggest open questions in the field, and people are looking for gravitational waves that come straight from the Big Bang. And it is perhaps they could be discovered tomorrow. There are big new experiments that are going online recently, and the data is being analyzed, so stay tuned. Perhaps there will be a major discovery. So a summary of what we have learned that the universe is expanding, the expansion is accelerated, there is dark matter and dark energy. We have learned that something that is discovered is never named after the person who discovered it. And that's how I want to end the talk. So thank you very much.
Okay, there were already many questions, but maybe there is some more. Is there any other? Yeah, at least one, two. Wow.
At one point, you painted a picture of the universe as this ever-expanding sphere. So I wanted to ask, what do you know about the shape of the universe?
Yes, so we don't really know. People have hypothesized various shapes, and you can talk about shapes and topology, which are two slightly different things. So let's talk about topology because it's more fun. So people don't know what happens if hypothetically you started walking in that direction for a long time. People don't know whether you would ever come back the other way in some sense. So it is possible that the universe has the same topology of a sphere, that if you go around, you come back on the other side. As far as it keeps expanding, we have no way to tell, because if you walk away from us, we will never see you again. So you cannot walk back. But in terms of the question of what is the shape of it, people have made various proposals. Unfortunately, because the expansion is relatively fast, we can never really see. As far as we can tell, the part of the universe that we observe does not have any interesting topology, but it could be that we are just not seeing enough of it to see that it comes around. And people have proposed many more complicated things than just the sphere. but so far there is no evidence for it.
At some point, you mentioned that the more space there is available, the more dark energy there is. And if our universe is expanding, does that mean that the total amount of dark energy is also increasing?
That's correct, yes. So the reason why, so one candidate, yes, that's exactly as you said, it is the total is increasing. What remains constant is the density. So the density is how much there is divided by the volume. So that is remaining always constant, but if you make the volume bigger, the total becomes bigger. In fact, that's why this object that I named the cosmological constant was called the cosmological constant, because the energy density is constant. And you should really contrast that to matter. When you put a kilo inside the box, as I said before, it is still 1 kilo when you make the box bigger, but the density has gone down because now you have 1 kilo but a bigger box. So it is the density that remains constant, but the total continues to grow. It's a pretty surprising fact.
Okay, thank you.
It means energy is not conserved?
Energy is not conserved. So energy conservation in an expanding universe is a very tricky concept. So there are 2 ways to try to discuss it. Perhaps the fastest way to answer your question would be, you're right, it's not conserved. In fact, when we see the light that comes from the cosmic microwave background or maybe from the next nearby galaxy, it is redshift. So where did the energy of light when it started go? And the answer is that energy is just not conserved, so it didn't go anywhere. Mathematically, people have tried to find more satisfactory answers to this. So there are more complex answers to the questions in which you try to define a certain notion of gravitational energy, and you try to find a balance between gravitational energy and non-gravitational energy. So other people might have tried to answer this question saying that the energy, the dark energy that is created by the expansion is actually subtracted by the gravitational energy. I don't think that this type of explanation has been fully satisfactory at the moment. But
you explained here.
yes.
I have this question because you explained how the expansion increases its speed, so the further. So when you were showing the sphere, I was thinking then if we look, the further we look, the more into the past we look, right? Because the light travels at certain speed. But then if the sphere is expanding, then probably some of the parts of the universe have already fallen behind the cosmic horizon. How does this, so we would not be able to look into the beginning of the universe. Isn't this theory about the inflation contradictory to us looking into us thinking that we have seen the beginning of the universe by looking into the furthest galaxies?
Not really. So what you cannot do is observe very far away, but you can always observe back in time. So as long as you look at something which is not too far, you can see it very early on. So we can see the beginning by looking at something which is not too far. So there is a difference between time and space. Maybe to draw it in terms of a drawing, if it is not too confusing, if we are here, and this is the Big Bang, this is what we can see. We cannot see this, but if you look nearby enough, then you can see all the way to the Big Bang. So we cannot see the whole of the universe, but this part we can see as far in the past as we want.
According to me, it would be interesting to introduce some notion of equilibrium. Every system tends to get an equilibrium, and the universe is not different. It means that the universe is getting some sort of equilibrium. According to me, the particular properties of time suggest that the universe on its way to this equilibrium is continuously getting rid of mass. Not matter, but is getting rid of mass. What do you think of it?
Well, as a scientific theory, it should be formulated within language of mathematics, and it should lead to predictions. So I'm happy to comment if it makes some predictions. Otherwise, I'm not sure I have much to say about it.
So I have like just one question, because you firstly mentioned that pretty much from like above 150 years ago we realized that the space and time is actually expanding and not is static. But why is it so that people thought like since the Newton's times they thought that the whole universe is static? Because like shouldn't they at least think when we've got two masses and we've got the Newton's law like of gravity, they should get closer to each other and the universe should actually shrink?
Yeah, absolutely. That's what they should have thought, and in fact that's what the equations told Einstein. But Einstein really didn't like that answer, and so he fudged with the equation and added the cosmological constant because he didn't like that answer. And he realized that if we add that constant, he could get a universe that doesn't expand. That was his reason. It's hard to know why he didn't like that answer. It's a bit strange to think that the universe has a beginning, and maybe that's what he didn't like. Maybe it was an element of the cultural discourse at the time between people thinking about a religious vision of creation, and certain scientists didn't liking the idea of creation, which would imply perhaps the existence of a God. So there must have been some cultural undertones to that discussion. Fact is that many people disliked the idea of a beginning and needed really hard evidence to start believing in a model like the Big Bang. And until the discovery of the cosmic microwave background, even though Hubble has this idea of the expansion, people still thought that maybe you can still explain an infinitely existing universe, a static universe, in that constant. But when the cosmic microwave background came up, people finally embraced this idea that it must be the Big Bang theory, the correct description.
Thank you. You already mentioned some religious aspects, and I would really love to ask this question, what was before the Big Bang? But I don't expect you to answer this question, because here we have physical, approach. So physics, philosophy, this is somehow connected, yes, but still quite often quite difficult to talk, to find this common ground, let's say. But about this expansion, really, I think if you, as scientists, think about, is there any link at the end to the beginning? Is there any kind of time, place when it collapses somehow? I don't know which words to use, but is there any chance to somehow connect it?
Yes.
And one extra thing that I would like to ask this question is, there are so many people now, and we think of so many issues, and do you think we can somehow say that our thoughts are energy, and this is about this expansion also, that there's more and more people, more and more thoughts, more and more relations, matter, energy, then we comes to Einstein.
Yes. So when physicists talk about energy, which is a word that is used in the common language to describe many things, for example, my father-in-law is a very energetic person. But when physicists use the word energy, it has a different meaning from the way we use it in the normal context. It has a mathematical meaning. It usually describes some quantities that are conserved during the evolution. So as far as whether more people mean more energy, I would say there is not really a connection in the way that you mean it, or in the standard physical meaning of energy, but perhaps there are other meanings of energy that you can give to it, within which it could make more sense to think of energy being related to people. But at the level of what physicists would call it, energy is locally is conserved, is not really conserved in the expanding universe, and the amount of people don't make a big difference because it's a small amount in the cosmic total. The other question you had, which is many people find somehow appealing, that if the universe is expanding now, it should at some point stop and come back to it. And there are various models that have been proposed. Some of them go under the name of cyclic models that, funnily enough, come and go out of fashion periodically. In some of them, there is a big bang, and then there is a big crunch, and then after the big crunch, there is another big bang. The main obstruction that those type of models have faced so far is the one that I mentioned before, is really the law of, the second law of thermodynamics, the general growth of entropy. So as far as we can tell, broken things don't go back together, so it's hard to imagine that there would be a way in which we could go back to the start. So none of these theories have really been able to explain in what sense things can start all of a sudden going back together. And so it's hard to imagine that even if the universe crunched back together, the entropy would be reverted. And if it wasn't reverted, the universe would just look very different from how it was at the beginning. Yes, please.
We know the universe is expanding, and it's possible it's explode, and it's going to, we have two universe. Like it's this rubber we saw, and we expanded, and it's explode and make two rubbers.
Oh, so like the rubber band will break apart. No, as far as we can tell, the expansion of the space-time is being created. So the rubber band is stretched, and as it is being stretched, more rubber band is created, so it can keep on stretching. So it's an infinitely stretchable space. That's what the laws of nature as we know them now tell us. It could be that we understand things differently, but so far we haven't seen that there is, in the laws of gravity as formulated by Einstein, there is no breaking point. Space can be created by an infinite amount and can be stretched by an infinite amount. So we don't expect it to break at any point, as far as we understand.
Hello, hi. Maybe it's a more personal question about your views, because you said there are some experiments being done while we speak. So what are you most excited about some in near future, or maybe even in your lifetime, to be proven or unproven or whatever?
Well, there are many things. Maybe I'll mention a couple, one related to my work and one that is not related to my work. One that is related to my work is that if they manage to see gravitational waves coming out of the Big Bang. So these are the so-called primordial gravitational waves. They're similar in nature to the gravitational waves that we have seen so far coming from the collision of black holes. They've been discovered almost 10 years ago. They got the Nobel Prize a few years ago. And so those we have established, and actually we're seeing them routinely now, maybe between 50 and 100 times a year, we see a new one. But what we haven't seen is whether it was the fabric of space-time during the Big Bang itself that was oscillating. And people will improve their ability to look for these objects by a factor of 100 in the next 10 years or so. And so there is a large discovery potential if we are lucky. So that would be my hope. I would be very excited about that. The other thing that I wanted to mention, which is not related to my work, I haven't said anything about it, is now the field of exoplanets has exploded. In 1994, we are discovering for the first time in human history planets outside of the solar system. And in the 90s, we found 1, 2, 3. Now we have more than 5,000 and counting. And so we're getting better and better at seeing exoplanets. The recent images that were also in the media from the James Webb telescopes and other measurements. What I think is plausible within my lifetime, fingers crossed that I live long enough to see it, is that they would be able to measure the chemical composition of one of these exoplanets, perhaps through the absorption lines that come from it. And perhaps if there is other form of life in the galaxy, they would be able to see if the chemical composition is the one that you expect from the primordial universe, or it has been altered by some form of life. So that would be one of the most exciting discoveries, to find extrasolar system life, or perhaps within some moon of Jupiter or something like that. Yeah.
Well, maybe let's make it last question or last questions, because we cannot stay too much long, but yeah.
So I thought about the possibility that in galaxy there is some possible way to see or somehow feel the Big Bang. It's like very, very far away, but like how the music is coming,
moving, propagating,
moving.
yeah.
Yes, and Big Bang is still moving,
Yes.
as I think. So there is somewhere we can still feel it.
Yes. So people have tried to do that, and they tried to do it in two ways. The first thing that they tried was using light, because after all, light is the thing that propagates the fastest. And however, it turns out that there is a big wall between us and the Big Bang, and we cannot see through it. So if you think of this as being us now here, and this is time, and this is being the Big Bang, and we are living here 13.7 billion years after the Big Bang. There was a moment in time at about 370,000 years after the Big Bang, where the universe had a big transition from being opaque to being transparent. So with light, we can easily see all the way until here. Any point we like, no problems. Piece of cake. In fact, we take this measurement. But beyond this wall is like looking through a cloud. You cannot see anything that is behind. This is when, for the first time, electrons and protons combine together to form neutral hydrogen. And when there are charged particles around, the light doesn't like to travel because it bumps into it the whole time. So we have a thick wall beyond which we cannot see. So the best way to see the Big Bang is not using light. We can only see back to 370,000. But then people said, well, why cannot I hear it? Maybe there is something that is vibrating that propagates better than light, and there is, which is gravitational waves. So the answer to the previous question was, if we were able to see gravitational waves, they would be coming all the way here, and because they interact so weakly, we would see them all the way to the Big Bang. So you could hear the sound of the Big Bang in gravitational waves.
Yeah, there was this last or second question in this row.
Yeah, so I have a question. You mentioned that the universe is like a sphere and that it is expanding to the future. And I was wondering if the universe is like expanding inside of something. Is it like some sort of energy? So if it's at some point there was like just a spot and it was surrounded by something and then it just kind of started expanding. Is it something that we cannot see?
No, it's not really expanding into something or away from something. That the best notion is that it's expanding into the future and away from the past, but there was not a point with something around it and the point grew up. That is not the right picture. Maybe it could help you to visualize it, but it doesn't help you to describe it in practice, what we observe. So we have various mental constructions to learn about things in which we try to compare something that we learn, something new, to something that we know. And every mental construction is an approximation. This is some approximation, what you are proposing, but it's not a very precise one. So it's not a very useful mental picture to have about the Big Bang.
Okay, great. I think we can thank the speaker for the lecture and all the answers, and also we thank the audience for all the questions. So
yeah, thank you.
Thank you very much. And the next lecture will take place in already 3 weeks during this Festival of Science, Festival Nauki, September 26th. It will be announced very soon on our website, so hope to see you soon again.